Hey everybody, my name is Rob Hayes. I am on faculty at NC State University in the Nuclear Engineering Department. Some history about me: I was born in Provo. Went to the University of Utah. I was born poor, raised by a single mom. Put myself through school, graduated with a whole bunch of debt because I had to work. So I did a stint in the Navy, and I took 5 years, did a double major in math and physics. Realized that you don't really make a lot of money with degrees in math and physics, so I thought I'd get a master's degree, maybe that would help. Got a master's, took me 3 years after that because I was working. I realized that's not much different than just a bachelor's in math or physics. And so I realized that I needed to go into engineering, and there, lo and behold, at the University of Utah, they had a graduate program in nuclear engineering. So I spent another 2 years and got my PhD in nuclear engineering and went off into industry. At that point, went and worked in New Mexico. Worked at the Waste Isolation Pilot Plant. It's a geological repository for transuranic waste. I got his license from the Environmental Protection Agency back in 1999 to receive transuranic waste. And I went down there shortly thereafter in 2000 to help with at the time I could only receive contact handled waste. And so I went and did all the radiological engineering necessary for them to start receiving remote handled waste. And so they received both remote handled and contact handled waste there. I did all of the nuclear and radiological stuff that was involved with the remote handled waste. While I was in industry, I became certified by the American Board of Health Physics. So I am a certified health physicist in the state of New Mexico. That makes, by law, at least at the time, that meant that only a certified health physicist could be considered an expert in environmental radioactivity, something I'm very familiar with. I also got my license to practice engineering in New Mexico in nuclear, and I also, when I then later moved to Nevada, got licensed there, which means that again, by law, you can trust my calculations for your safety. Just like with any, the same thing we do in many other professions, legal, medical, so forth, dental, you have to have a license to practice something that the public relies on for safety. We're going to control that, and you have to demonstrate proficiency so that we can actually trust you with our safety. While I was in industry, I also went and moved to Las Vegas. I spent some time there working for the contractor for the former Nevada test site. What I did there was emergency response. It was my own team that got sent to Fukushima. So I did radiological emergency response there. I was also on the RAP team at WIP, which is again just emergency response, doing consequence assessment. What I'm going to be showing you here is basically what I do teaching and researching. That's really my expertise. So when I went to NC State, I put together, so it's the first academic nuclear engineering program on the planet. 1951, it was part of their engineering physics department, and there was a program in there to do nuclear. And as a result, in 1953, we had the first academic research reactor at North Carolina State University. The current version that we have is just down the hall from my office, literally. Just walk across the hall, take a little turn, and there's a 1 megawatt nuclear reactor right there across the hall from my office. While I was there, I put together an undergraduate minor in health physics and a graduate certificate in health physics. Health physics is like code word for radiation safety and radiological protection. That's what I do. That's what I'm an expert in. And while I was doing that, I also, at one point, I had a joint faculty appointment with Oak Ridge National Laboratory. Right now I have a joint faculty appointment with Savannah River National Laboratory because my research, you can see some of my toys up there in the bottom left, is doing nuclear forensics, radiological emergency response, nuclear nonproliferation. That's where a lot of my research is focused in. And this right here on the left, it's very pretty. It's an electron paramagnetic resonance spectrometer. Oh man, I could go on all day about what I do with that. And this right here is a thermoluminescence and optically stimulated luminescence spectrometer. And again, I literally do teach a course where I just teach students how to use these things. An entire semester, just to go into the research you can do with those. They're quite fun. I also am now an associate editor for the journal Radiation Physics and Chemistry. So I decide what even gets sent out for review, if at all, based on whether there's going to be interest or it's actually sufficiently novel to warrant that. And then this QR code is something that's also a little bit interesting. And that QR code is because while I put together this program for students for health physics, a lot of them did research in what was considered, and still is considered by the American Nuclear Society, the #1 grand challenge in the United States and the world is public communication. And they convinced me, these brilliant graduate students that we have, that the only way to really do that effectively today is on social media. And after hearing them say that for oh so long, during lockdown, I finally went ahead and did it. And so I have a TikTok channel where I actually will post these little videos that, based on my research, to address public concerns. And so that kind of is what instigated all of this. I got involved in public communication. And so here I am today, again, doing public communication. This is what I'm going to talk about today. This is the technical part. That's the part that I really like. We all do research in what we like, and we do the work that we like if we're lucky. And so I like the technical part. I like the math, I like the physics. That's what got me into this in the first place. So we're going to go through this, and we're going to start with, this might be the worst of them all. So I've been told I need to really make this simple, because we're going to use a lot of this in this lecture. So I'm going to come back to a lot of the physics that I have here in this slide when I talk about all of the things that are related to radiological risk. So probably the most important one, and hopefully the simplest, is this one. Whoops, I want to go forward. Is this one here on the left. And so at the top, what we have is we have a fission reaction taking place. So if I have this thermal neutron, I have a thermal neutron comes in, and a uranium-235 nucleus, an isotope of uranium. We'll talk about what isotopes are here in a second, but an isotope of uranium-235, if it absorbs a thermal neutron, it has a certain probability of fissioning. And if it fissions, you can get all kinds of different fission products out of it. Here's some examples right here. You see barium-139. I'll help you explain what that is. And krypton-95. Those are possible fission products that can come from fissioning uranium-235, that isotope of uranium. Now, that's a bunch of gobbledygook. What's going to be more relevant to all of this is this number right there, 200 MeV. That means 200 million electron volts of energy is what, on average, you're going to get. You're going to get something like that for every uranium-235 nucleus you fission. 235 million electron volts per atom. That's the kind of energy potential that you have in nuclear. And I'm going to explain why that means you have high energy density. The reason you have high energy density from that is if I did combustion or any other chemical reaction, basically all of science and engineering, almost all of it, is just juggling valence electrons. What are valence electrons? Those are the outer electrons orbiting an atom. And when I do chemistry, all I'm doing is rearranging those. Any kind of chemical reaction, just rearranging those outer valence, not the inner shell electrons, which are the ones that generate X-rays, but the outer shell electrons, the ones that generate visible light, that are reflecting the light off of everything we see, those outer valence electrons. You're just moving those around when you're doing any kind of chemistry. Any other kind of science, almost invariably, is just those outer electrons. And the energy difference that you have, especially this particular reaction right here, burning methane, burning natural gas, you get about 1 electron volt per atom that's taking place there, with all of the hydrogen and the carbon and the fuel, and then the oxygen to oxidize it, and then get it spitting out the carbon dioxide in the water. You only get about 1 electron volt per atom. So 200 million electron volts per atom versus 1 electron volt per atom. That is many orders of magnitude. That is energy density. I can get a massive amount of energy from a very tiny amount of materials if we go with nuclear energy. That's energy density. That is phenomenal. And so I'm going to say some things that are going to be kind of hard to believe. So I'm going to start with one right here. I'm going to start with one right here. I'm going to talk about, because what I deal with a lot are myths. Flat out, flagrant myths regarding misinformation around nuclear energy. So I'm just going to throw one out here right now to set the stage for what kinds of things can happen when you don't understand radiological risk. Because there's such a vast amount of energy density there, it can be hard to really get some good information. So here's a fun one. Who's heard about the Fukushima wastewater being dumped into the ocean? So a few people, I've heard of the Fukushima wastewater. Now, the reason why I bring that one up, people haven't been asking questions about it. I thought I'd bring this up because this is a real quintessential myth. Now it's true. Fukushima wastewater is going into the ocean. It's also true the International Atomic Energy Agency has been monitoring that from the beginning. It's also true that the levels of tritium that are in that water are below the limits that are considered safe for drinking water. So if you've heard about the Fukushima wastewater going into the ocean, you've heard about potable water being dumped into the ocean and a big deal being made out of it. So let's get into the ones that people do have interest in. Most people don't care about Fukushima wastewater, but that kind of sets the stage about the misinformation that's out there, the hype versus what's real. What we're interested in here, especially as academics, is what's real. That's what we care about. All right, now the difficult part, an isotope. So what we have up here is we have a chemical symbol. So this X represents the letters that represent the element. And that tells you basically how many numbers of protons are in the nucleus. When I have a fixed number of protons in the nucleus, that defines the element. That determines how many electrons are orbiting it. And the way that I put those electrons on there, based on the laws of quantum mechanics, there are only fixed ways I can stick them on there. They're limited, they're quantized. And when I put them on there, there's only limited ways that they can be rearranged. And those limited ways that they can be arranged is what we call chemistry. And everything that goes with it. Chemistry, biology, geology, all those disciplines are based on how we can rearrange these valence electrons. And so that's what the Z is. So we usually don't list the Z because it's kind of redundant. The Z already tells you what the chemical element is. But this top left number, that's the atomic mass, the atomic number. That mass number tells you how many neutrons and protons are in there. And why we do that is because I have for many, many elements, multiple numbers of different neutrons I can put in there and it still not be radioactive. I can have some for something like, we'll come back to this later, neodymium. Neodymium, if I have this isotope, neodymium-147, that means I've got 60 protons, but in order to have 147 atomic mass units, then I've got to have 87 neutrons. So the total mass, isotope is defined as neodymium-147. That's all it is. So hopefully I got that really simple, because we're going to come back to that, and we're going to do it right now. And that's what I have in the middle thing. This graph right here in the middle shows you the distribution of the isotopes that come out of fission on average. So if I'm doing fissioning, if I have a nuclear reactor, and I'm fissioning it like the trigger reactor up at the University of Utah, that research reactor that they have, they're fissioning with thermal neutrons, and so you get a distribution of masses, atomic masses, that looks like this. So mostly I'll get things that are around 90 and 140. And you can see this one's around 140 and this one's around 90. And so that's what you get when you do fission. All right, so that's a fingerprint of fission, is by looking at those isotopes. So we're going to come back because we're going to talk about isotopes, especially when we talk about uranium. Uranium isotopes are a big deal as well. All right, so let's go back at the fuel cycle. This fuel cycle, something that I know as a health physicist, is that every step in this fuel cycle, I generate some radioactive waste. Different kinds that I get at different stages. And they all have different risks. Some of them are internal and external, and some of them are for inhalation or ingestion. Most of them are for external exposure, for the most part. But not always, there are definitely exceptions. So we can start with digging up some dirt. It's basically how we get any metal. Everything that you see around us, everything that we have control that's either grown or it's mined. So you either give your resources to build houses and infrastructure and amenities, you either grow it or you mine it. And out west, we do a lot of mining. I know when I lived in Nevada, one of their claims to fame was that if it was an independent nation, it'd be the second largest silver producing nation in the world, because there's a lot of mining. We're out west. It happens. But that was their claim to fame in Nevada, for all the silver mines that they had. It's called the Silver State. Like here in southern Utah, historically, we would dig a hole, put out some dirt, and that dirt would have elevated levels of uranium in it. Through the eons with geology, you get like different dissolution rates, different rates at which it can go into magma, and you get differentiation of the elements, and you can get different parts of the earth with different concentrations of particular minerals based on them. And that also happens with uranium. So if you find a place where you have a lot more uranium, you can go dig it if you want uranium and you want to dig that up and utilize that as a resource. Once that happens, it's then got to go and be milled, right? Milling is where you basically crush it to fine powder. so that you can basically take all of it, just throw it on the water, and it would all float. Those rocks would just float because it's been milled so finely. But then you have to leach out the mineral component. You don't want the silicate. The silicate is just silicate. It's just fine silicate, maybe turn it into clay, I don't know. You don't care about that, the silicate dioxide. What you care about is the mineral. That's what's interesting. You don't want any of the organic stuff, you burn that up, you want the mineral. And then that mineral that comes out, if you've refined it properly, is going to be this U3O8, the yellow pigment. That then goes off for a different chemical process, where you've got to calcine it, then you've got to fluoridate it, you turn it into uranium hexafluoride. The reason why we turn it into uranium hexafluoride is because at ambient temperatures it's a solid, but if I heat it up a little bit, it turns into a gas. It's really easy to turn it into a gas. And then you do enrichment. So the fissile component of uranium-230, of uranium, the one you use in a reactor, is the isotope uranium-235. It's got 92 protons, but a different number of neutrons. And so when you want to do a nuclear reactor, you want more of the uranium-235 than the uranium-238. Uranium-238 is about 99.3%. It's the majority of all the uranium that's out there. Now, we use the different mass of those nuclides to do this enrichment. Once we do that, then we're going to convert it again. Now we convert it into uranium dioxide. Uranium dioxide is basically just rusted metal, but then we'll compact it and sinter it. Sintering it is the same thing we do with any other ceramic. You take that rusted metal in a fine powder, you compact it, you heat it up so that you get some little bit of diffusion across the grain boundaries, and you get adhesion, and it becomes a ceramic, a hard ceramic. And that's what we do with the fuel, the UO2. Once we made that, it goes into those little gummy bears, goes into the reactor, makes electricity. And right now, what's the law in the United States? The law in the books is that it's going to need to go to a geological repository. Now, the rest of us would all like to see it be recycled. I mean, you've already spent all that energy digging it up. You spent all that energy turning it into uranium hexafluoride, and then uranium dioxide, and then all of that effort. You don't want to just throw it away, but that's what right now the plans are in the United States. Now, there have been some executive orders that have changed that, but we'll see whether we actually do. I am hopeful. Now that at least one political party said we're going to start recycling it, I think both will. I think that that's something that resonates with most of us. It just doesn't make sense to throw it away. We should recycle it. Let's put in some R&D, make it cost effective, make it attractive, and then industry will follow. That's the philosophy that most of us have anyway, is that we definitely should recycle. Then we don't need to dig up anymore. Plus we can use all of the waste depleted uranium hexafluoride that came from enrichment and turn that into electricity. That would be wonderful. But that's just hopefully that we'll be able to do that. Now, one of the big mysteries that some people have is, how does a nuclear power plant work? It's like this is some kind of space age technology. It really comes down to just replacing the heat source that I have in a thermal reactor. So most of a nuclear power plant is no different than a geothermal plant, a natural gas plant, a coal plant, or an oil plant. The only difference is the heat source.